Bonsai 27B compresses a reasoning model enough for a high-end phone. 27 billion parameters in a language weight file under 4 gigabytes. That sounds like a free local upgrade. But fitting a model into memory is not the same as preserving what made it useful. What happens inside an LLM pushed to 1-bit weights? And what does Bonsai sacrifice for a phone-sized footprint beyond the launch headline? QN3 6-27B is the baseline, a dense, multimodal model with roughly 27 billion language parameters and hybrid attention. In 16-bit precision, its language weights occupy roughly 54 gigabytes. That excludes phones and many laptops before inference begins. A conventional 4-bit package is smaller, but PrismML measures its QN build at 17.6 gigabytes, still beyond a normal phone application budget. Weights are only the first layer. During real inference, the runtime needs activations, working buffers, and a cache that grows with the conversation. PrismML derives Bonsai from QN3 6-27B and keeps its 64-block hybrid backbone. The architecture is unchanged. Binary Bonsai is the smallest variant. Across the language network, its weights take 2 signed values, with 1 shared scale per group. Ternary Bonsai adds 0 as a third value, giving the compressed model a way to represent weak connections inside each scaled group. PrismML publishes gguf and MLX packages under Apache 2. Binary favors footprint, ternary spends memory to recover behavior. In a 16-bit tensor, each weight can represent thousands of numeric levels. Every parameter carries its own comparatively precise learned value. Binary compression replaces that range with -1 or +1. It keeps direction but discards each weight's magnitude. Bonsai puts 128 binary weights under one 16-bit scale. Each sign then shares one common magnitude. The scale has a cost. One sign bit plus its amortized share equals 1.125 effective bits per weight. Ternary weights choose -1, 0, or +1. 3 states preserve more information but cannot fit in 1 bit. Ideal ternary storage is about 1.71 bits per weight. Current packages use 2-bit slots and add alignment overhead. This is not blind conversion after training. Quantization-aware training lets the network adapt while its weights are forced into the restricted alphabet. The trade is fundamental. Fewer values move less data but narrow how precisely the network encodes transformations. During autoregressive generation, the model produces one token, feeds it back, then repeats the network to choose the next. At small batches, each step streams essentially the full weight set while doing little arithmetic per byte moved. Decode speed therefore depends heavily on memory bandwidth. Moving fewer weight bytes per token can make the same hardware faster. Binary Bonsai cuts resident language weights from roughly 54 gigabytes to 3.9. The memory bus carries far less per step. Packed weights help only when kernels consume them directly. Unpacking into wider values before matrix multiplication can erase the advantage. Theoretical bit width describes how compactly the language weights themselves are represented. It does not describe the memory required by the complete running process. Binary matches its ideal size. Ternary is about 5.9 gigabytes in theory, but 7.2 in its deployed container. Add runtime buffers and activations. PrismML reports about 5.2 gigabytes peak memory with a 4,000 token context. Longer context expands the key value cache. At 100,000 tokens, PrismML reports 11.6 gigabytes uncompressed. A 4-bit KV cache cuts that term sharply. The vendor table reports 6.8 gigabytes at 100,000 tokens. Vision and speculative decoding add optional packages, a 0.63 gigabyte vision projection and a 1.8 gigabyte drafter. In PrismML's thinking suite, ternary Bonsai retains about 95% of its full precision QN reference at a smaller footprint. Binary retains about 90% in the same vendor harness. The average hides larger drops in instruction following, tools, vision, and reasoning. Those are useful engineering results, not independent confirmation. Aggregate retention does not make every answer 90% as good. One repeatable community benchmark found a steeper ladder from 4-bit QN to ternary and binary, with the largest damage in math and Persian. Benjamin Marie's coding evaluation found another cost. Bonsai used up to 14 times more reasoning tokens on some tasks. Runtime varies by backend. Kernel maturity, prompt processing, context settings, and hardware can dominate experience speed. Tool use evaluations show promising completion, but also retries and failures. They test specific harnesses, not universal reliability. That distinction matters most for agents. One user request can trigger dozens of separate model turns, tool calls, observations, and revised plans. If compression makes every token cheaper but the model needs many more reasoning tokens, some of the latency and energy advantage disappears inside the loop. Agent history grows. Tool output and evidence expand context, making KV cache size and prompt processing recurring costs. When the entire loop stays local, private files need not leave the device, network round trips disappear, and repeated calls avoid a metered remote API. But the best local agent is not the model with the smallest download. It is the model runtime pair that fits, stays coherent, and finishes the workload efficiently. Bonsai makes an extreme operating point genuinely usable. A dense 27 billion parameter network represented end-to-end with binary or ternary language weights. Its real limit is equally important. A phone-sized checkpoint does not guarantee full precision quality, cheap reasoning, mature kernels, or phone-sized peak memory. So evaluate the whole system: weights, cache, runtime tokens, task success, and hardware. Bonsai makes stronger edge models plausible, but the trade-off remains the product.